We will start the session in few minutes. Hello, good evening, and welcome back to the week 8 doubt clearing session on fundamentals of additive manufacturing. So, this week's presentation was all about the YAM process. If you remember that we already have talked about what is the directed energy deposition, and WAM is a type of directed energy deposition process where we use electric arc as a heat source, and metal is the material that we are using here, and the material will be present in the wire form. So like that, it's called wire arc additive manufacturing. So now WAM concept, I'm not pretty sure, but the WAM concept is almost similar like the welding concept. If we think about a welding process, then if this is my T joint, so this is one part, metal part, and this is one metal part. And if I want to join these two metal parts, first I will place the metal parts like this, fix it with the appropriate fixture, and after that, I will deposit the material here like this till the end of the part. If my part is looking like this, for example, this is one plate and this is another plate, and I want to join these two plates as a T joint, then I will deposit a material like a metal in this region. So now, why not to use the same concept for printing a whole part? Because here there is two processes. If you remember from BTech days, that there is MIG, metal inert gas welding. There is TIG, tungsten electric arc gas arc welding. In MIG, we use a consumable wire. So through the wire only, we supply the electric current and we produce the arc. And because of the arc, the metal wire get melted. And as we just move the torch, we deposit that metal in that joint and the parts get joined. In case of TIG, we supply the metal wire not coaxially, off axis, because in tungsten inert gas arc welding, the tungsten is not the consumable one. So we use it as an electrode to make the arc, and the arc is a heat source. So we have to understand the concept that whenever we are talking about metal additive manufacturing process, we are talking about two things. One is the energy source, how you are putting the energy, whether it's an electric beam, electron beam, or it's an electric arc, or it's a laser, or it's induction heating, or it's a resistance heating, or it's a UV light. So in metal, UV light is not powerful tool, but we have seen in FDM process that resistance heating is the one who is helping to melt the metal. So here in this process, of welding, we are using the electric arc. And to produce an arc, we need a cathode, we need an anode. So cathode and anode, if they are joined together, then the current will flow. And if I make a little bit distance between this cathode and anode, then the electrons try to jump from one and another. If you supply voltage or high voltage between these two poles, then we get the spark. And arc is a constant thing, like we are not touching it, we are maintaining a gap and we are making a constant arc by supplying the constant voltage. Like that, because of the arc, there will be a very high temperature produced at the tip of the metal wire. And because of that high temperature, the tip of the metal wire will get melted. And eventually, if you move the torch from one end, if this is the torch, and if you move this torch from one end to another, you will deposit the material. When the material is supplied off axis, it's called the tick process. So this process, if I just repeat this process in such a way that now instead of a T joint or instead of a lap joint or butt joint, I have taken only one plate. I just deposited that one track of metal here. This is called a track. This one track I deposited to weld this T joint. Now here, if I just deposit the track on the top of a substrate, then that will be a bead for my additive manufacturing. And now with the overlap percentage, after some distance, if I print that same bead again, then now I have some width of this two bead, right? Now, if I print the same bead again on adjacent to the previously deposited bead, I will again increase the width of the total deposition. Like that, now if I print till here, like the 10 beads, then I can call it as a layer for my additive manufacturing process. Now, if I move the torch up and now my deposited bead is my electrode, one electrode, and the wire is the another electrode, then I can subsequently print another layer on top of the first layer. This is nothing but the layer by layer deposition of additive manufacturing. So this is how the principle of the additive manufacturing, how it works. And using the same welding concept, people have developed this wine setup. So in case of welding, what we see is how much strength the weld joint is having. So we can do some stretching, like tensile testing of the welded joint to see how much strength the bond is having between these two thick plates. We can cut in the cross section. So if you cut the plate from here, then you will get a bead like this. This is the cross section. So if you now polish the cross section and see the microstructure, you can see how the grains are formed, what is the hardness of the bead. We can do more tensile testing and mechanical testing as well. So what is the conclusion? The conclusion is that I can repeat the process here as an additive manufacturing and do all the characterization and can prove myself that yes, welding concept can be used in the additive manufacturing process. So now let's see how WAM works. But another case is in case of welding, we are just depositing one bead, but in additive, we have to deposit multi-bead and then multi-track, multi-layer. So in case of multi-bead, there will be overlap percentage between these two beads. Okay, so that means we are kind of remelting the previously deposited bead. And when I'm talking about multi-track, like on top of it, there will be another layer, multi-layer, sorry. Then again, we are remelting the top part of the previously deposited layer. So that means our layer, the top part of the layer is getting remelted. So there will be grain, there can be grain refinement, there can be grain coarsening also. It depends what are the process parameters. And as the side part of the bead is also getting remelted because of the multi-track, there will be grain refinement or grain coarsening. It all depends on the process speed and the arc energy and the metal that you are using, your gas. So it's inert gas. So the process is taking place at the presence of inert gas. So those things are also important and those things are highly influential in this process. So like that, if you cut the layer from the build plate, you can see the microstructure, you can evaluate the mechanical properties, and like that you can actually print a part out of this concept. So it's a little bit more complex in case of additive manufacturing if you're using the concept of welding here. Also, let me point out one another thing is establishing an arc is very difficult. We are doing just one track in case of welding, so it's easy process. But if you really want to deposit multi-track and multi-layer, it's gonna be very complex, and there will be the waviness in your printed layer. You need to have some optimized process parameter to have a very flat surface, and then you have to control all the process parameter all together to get a part. It can happen that for different layer you need to change your parameters so that you can get a very good deposition. So in this week's lecture, this is the overall concept of any metal additive manufacturing and more specifically VAM process. So in this week's lectures, similarly, if you classify the VAM process now, there will be this subsections of how or what material you are using. As I already have said, VAM is something where you're putting the you're establishing electric arc. That means metal, conductive material is the only option. And in conductive material, we know metal. So metal is the only option. We cannot print any polymer using this process. Now, the second classification is the material flow. Here, mostly it's continuous material flow because first of all, as I said, arc establishment is very difficult. And now if you want to do it on drop on demand, then you have to establish the arc again and again in a pulsed way, which is more complex. So why to make this process more complex when it's already complex? The material flow is gonna be almost continuous. Material kinematics, it's an option for the machine manufacturer. They can use anything to build it. Serial kinematics is a simpler way. Parallel kinematics can give us more degrees of freedom, and hybrid is giving us both the facilities of serial and parallel. Energy source is the arc here because we are talking about wire arc additive manufacturing. Support mechanism is no support or multi-axis kinematics. So if you are printing it with CNC machine with 3 degrees of freedom, obviously, because in the case of high overhang angle and overhang length parts, you have to put the support structures. But if you are working in a robotic system where the robotic arm is having equal to or more than 5 degrees of freedom, then it's good to go to print no support structure parts. The overall concept I have already told you. In case of this VAN process, the major or the main thing to understand is when don't call it as cathode anode, just call it in a simple way that plus or minus. So in case of plus or minus, if you talk, then in case of consumable electrode process, that is the metal inert gas welding, metal inert gas additive manufacturing, then your metal is going to be deposited. So always remember, from the minus end, the electrons get deposited or the electrons get emitted, sorry. And from the positive side, plus cannot get emitted. So what happens is the material get eroded. Like the material comes out of the metal. So when you are talking about a process where you're welding, your electrode is consumable. That means your electrode has to be positive. And in the positive side, all the energy goes to the positive side. That's why, like if you compare the negative and the positive side, the positive side gets the more energy because of energy or gets the more heat because of which it gets melted. So in case of consumable electrode metal inert gas welding, we will make the electrode like the wire as a positive. And when you're talking about TIC process, that is the tungsten inert gas, there my electrode need not to be positive because I don't want my electrode to be melted because that is the non-consumable wire. My wire is fed from outside. So that's why we make the substrate as the positive. Now substrate will not get melted because there will be high heat. We need some dilution in the build plate. So the build plate is now getting more heat. So the upper surface of the build plate will get the heat and get melted from top surface, which is needed in this process to get the dilution between the deposited bead and the build plate. And eventually, when you subsequently print other layers, your previously layer need to be remelted on the top from the top portion, and that can be done easily in case of that process where I have made the base plate as the positive side. So that is the basic concept. If even if you forget that what is this direct electrode, negative, positive, what are the things, you just remember that if I have a negative and the positive pole, negative pole will emit electron because it has more electron. That's why it's negative. And the positive pole will be decayed. So the positive from the positive pole, the deposited material will come. And from the negative pole, only electron will come, no material decay. So in MIG and TIG process, the process takes place in an inert gas atmosphere. Like from the nozzle or from the outside nozzle, we continuously feed argon gas or nitrogen gas. It depends which metal you're printing. Because we do not need the oxidation to happen in your deposited part because oxide formation means brittle phase formation. The upper surface, the surface is gone. And if you're printing the another surface on top of the previously deposited surface, and now the previously deposited surface is all around or all about the oxide formation, then your part is going to be a waste. So we don't need any oxidation. We don't need any evaporation. We don't need any particle inclusion from air. We don't need any interaction of the airborne particles in my deposition during my deposition. So argon gas or nitrogen, any inert gas is sufficient to cover up the process. So with a high gas flow rate around 3 liter per minute or 5 liter per minute, we feed the argon or nitrogen gas to make the process contamination free and oxidation free. I'm not reading each line because it's quite a long lecture video. I would recommend you to please go through the lecture videos because there are a lot of information that professor has shared. Lot of equations were solved, how you can get a good deposition, how you can get a good bead, etc. And how and you can feel that if I'm talking about the melting of the wire and then depositing it layer by layer or track adjacent to another track, then obviously there is some mass transfer, there is some heat transfer, and to get a good deposition, you have to have an optimized parameter. And optimized parameter doesn't come randomly. You have to optimize it with the base of some logic, some physics, and the physics is always repeatable. So that means you have to find out how it is coming. So the how answer will come from an equation only. So there are some mass transfer and heat transfer equation, how you can get the particular shape of bead using which combination of parameters. So just go through the lecture there. All the equations are mentioned there. If you have any doubt in between, just stop me and ask. Or if you have already watched the videos and you have some doubt, we can discuss about it. So as I am talking about the MIG process or TIC process, the short circuit, deep transfer, globular transfer, spray transfer, pulsed spray transfer, rotating spray transfer, these are the techniques how you can transfer this droplet to the metal substrate, because I already said arc establishment is very difficult. And along with the arc establishment, your material is coming as a droplet, but the wire is getting melted. And coming on the substrate as droplet, and continuously the process is going on. So continuously the droplet is coming. If your printing speed is very high, then the droplet will not properly fall onto the substrate. Rather, it will fly off. It may fly off, it may get flew off, or it may get some distortion in the melt pool. The melt pool will not be stable. There can be gas entrapment in your melt pool, and eventually you get a waste. So the transfer mode of the wire after getting melted is important, and globular and spray transfer are some important way of material transfer. There are nice videos on it, so you can see. So as you can see, this was one bead, this was another bead, there is another bead just deposited. Now there is another droplet is getting produced, and it will also come here and will get deposited like this. And when you get this droplet formation at the end, you get this track. So this is track number one. Adjacent to this, there will be another track. And on top of it, if you repeat the process, you get the layer. So this is my second layer. Like that, it works. So modeling and simulation is also important. Just an extra point. Modeling and simulation is also important in these type of study, because before wasting the metal and resources, it's better to first see in the simulation how it's working, or to read the physics, that how the globular mode of transfer and spray mode of transfer is going to happen, and then decide accordingly which metal I'm going to print at which speed, so which mode of transfer I should approach for. So this is the process cycle of the MIG based WIME process. This much we all know. CAD modeling is the first thing. Then after save it in the STL file format, I'll orient the part in my slicing software, support generation if it's needed, then slicing. And after slicing, if I just press OK, the toolpath generation will take place. After that, it will go to the bead model library and deposition unit. So it's basically a computer where you are going to put your part, your sliced part, uh, in the directly in the machine. This computer is directly related to that machine where you are going to put your part, so that now the process parameters will be defined here in the bead model library. So what will be the overlap between tracks? What will be the overlap in case of in the vertical direction at the time of layer printing? What will be the arc length? What that is the standoff distance we call it in other process. What will be the current, voltage? What will be the deposition velocity? What will be the wire feed rate? Because the wire is similarly coming just how it was coming in FDM process. There will be pulley, intention, everything. So how the wire is coming at what speed you're moving the wire, at what speed you're depositing. So all this thing will be put in this software part. After that, it will come to the deposition. It can directly come to the deposition if you do not want to consider all the factors and you just want to print. Maybe your part will have some porosity, but it will get printed with a okay parameter or bad parameter as well. After deposition, rolling, peening, hammering, interpass cooling, then face milling. So what are these? These are the post processing. So the post processing now can happen in many ways. So in case of DED process, or especially in wire based DED process, as in case of wire DED, the bulk material is coming and getting deposited. So your deposition track will typically have the diameter and width in millimeters. Maybe you'll get a 3 millimeter bead, a 4 millimeter bead with a 2 millimeter height. So it's in millimeter. It's not a quite small bead. So now if you're overlapping the beads and printing that whole layer, your layer will have some undulation and waviness on the surface. The If you're printing with spray mode of transfer or any other mode, there can be some small agglomerated solidified particles on top of the layer as well. So now if you are going to print the next layer on top of this bad surface, or obviously your printing going to be worse. You will not be able to print the second layer. So for second layer, your first layer is acting as a build plate. Tell me if you're not understanding. For your first layer, your substrate is the substrate. But for your second layer, your first layer is the substrate. For your third layer, your second layer is the substrate. So if your substrate is not good, obviously the printing is not going to be good. So because of which, sometimes there you can find some machines where there is the feasibility to use any post processing such as subtractive manufacturing like face milling or kind of milling operation done on the first layer before going to deposit the second layer, so that now your first layer is ready to be acting as a substrate.
Excuse
So
me.
yes, yes,
And in that case, we have to wait till the uh, previous layer
is
get
cooled.
cooled.
Okay, so it's
Takes a lot of time, no?
it will not take lot of time because the milling it will be solidified very quickly because your scan speed is very high in case of additive, and the heat will still be there because of the conduction of heat, but you can start the process after 5-10 minutes because there will be
It is,
continuous flow of argon gas which is also helping for to the bead to get cooled down.
no, no, if it is like polymer additive manufacturing, then it will be okay. But here, it is almost the welding
Yeah, so
rod
it will be heated up. Yes.
3,
So
3 mm.
I can even give you the values. So
It's
for example,
really
in aluminium,
state, no.
yeah, so
It could go beyond its melting. For example, if you take stainless steel or some mild steel, it will be around more than this
1500.
one. Yeah.
Yes. Yes. So I can give you one value. So in case of aluminium, if you are printing, obviously the aluminium melting temperature is 662. It will go above 660, around 900 or so. Just after the deposition, we check the temperature for each layer and it comes around 300 to 400 degrees. Because of the fast cooling, it cools down that easily. Now, this 300 to 400 degrees centigrade is difficult to get cooled down because of its less heat gradient, right? Now, when you are going to do the milling operation, there will be continuous flow of argon. So that argon will also help as a coolant to cool down the bead. So when it reaches, because of the argon, if it reaches around 150 or 100 degrees centigrade, we can start doing the milling operation. And by that time, you will also change the tool from additive to subtractive. The build plate will go to the other side of the machine and it will also take some time. So by that time, if you continuously feed the argon gas to it, the problem will eventually be solved. But it's a good question that you asked. Did you get the answer? So it's
Sorry.
basically that when you're printing, even if the same machine is having the additive and subtractive part, it will not be present at the same place. So if at this location you are doing the additive, this is the nozzle, this build plate needs to go to this position, that is the first movement. Then there will be the tool magazine from which one tool will come, it will come down and then it will set its position and then it will start doing it, right? And this whole process will take some time. It is not that fast because you are working in CNC.
All are equipped in one machine,
Yeah,
both
all are
welding and
equipped in one machine.
CNC.
Otherwise, it's not possible for each layer or each 10 layers.
Yeah, yeah, yeah.
Yeah. So that is one possibility. So, and at this whole time, the argon gas was continuously fed. So that is
Yeah.
also kind of working as a coolant. So if your temperature comes up to 100 degrees centigrade, it's okay to start the process.
But sometimes sudden cooling is not desirable, no, particularly in
Yeah, but
thing.
if
And that
you
to
are,
some
as I said, The melting point of aluminum is 660. But obviously, so the temperature will rise till 100,000 or 900 degrees centigrade at the time of printing. The instantaneous temperature is very high, but just after the deposition, when we check the temperature, it's around 300 to 400 degrees.
But in the case of other metals like steels, it will be more than 1500, no?
No, yeah, 1500, but it will come down very easily because of its high heat gradient. In case of steel, it's even more heat gradient, and it's not even having that much high heat conductivity that like aluminum or other metals.
The thermal gradient will be more.
Yeah, if thermal gradient is very high, that means heat dissipation will be higher.
Yeah, that's
And
what I
also,
actually that sudden kind that much of cooling is not desirable.
no, it's
It leads
it's
to
okay
some
because
residual stresses. Again, some stress relieving kind of thing need to be
yeah.
given.
So if you are talking about additive manufacturing, you cannot help but getting a very high cooling rate because additive manufacturing is all about high cooling rate and high deposition rate, because of which you get a very smaller bead. That we already know and we agree, right? And now, if you are doing some deposition at a very elevated temperature, elevated power, then obviously because of the high heat gradient, the cooling rate is even faster. And that's why we are using additive manufacturing. And that's why, in case of stainless steel or so, we get some martensitic formation, we get some brittle phase formation, because of which the additive manufacturing process is mostly followed by the heat treatment to relieve the residual stress. So to dissolve this hard phases.
That means it is under during post processing.
Yes, during post processing. In case of this process also, we are doing the milling. So as soon as it cools down, and it will cool down very easily, so we can start the milling process. There will be no harm. Even in some cases, your subtractive manufacturing like face milling can actually uh, like decrease the residual stress because of its pressure, because it will put some pressure at the time of milling, which can actually relieve some of the residual stress. It can do vice versa also, increase the residual stress, but this is also one possibility. If somehow your part is having tensile residual stress, which is detrimental to the surface, which is detrimental to the part, and then you are doing pinning, like laser pinning or short pinning, you are actually introducing some compressive stress in that, which will even out the tensile residual stress. So your part will be better in terms of property and stress. Did you understand this point?
Okay.
Yeah. So this is the common thing that we see in case of additive manufacturing, that we get mostly compressive residual stress, which is good for the part. Tensile is not, but when we do the post processing, we basically relieve it, or we try to even out by incorporating the opposite stress in it. So
Ma'am,
after phase, yes,
is rolling and hammering all these things done to level the surface
both
after
away. So
deposition?
if you are doing it after the deposition, after the whole deposition, then two things. One is for the surface roughness, another thing is for the stress relief and subsequent property enhancement. And if you're doing the face milling in each 10 layers, that means you're just doing it to even out the surface and also to some extent relieve the stress. As I'm talking about the deposition process here, I didn't mention about the stress relief. But now when you will go towards the finishing of the part, we go to the heat treatment, because that is something you have to do after any metal additive manufacturing process. And after everything, your final part is ready for the application. Any more doubt you have on this slide?
What does NC stand for in NC file generation?
It's a numerical. So CNC is computer numerical coding, and NC is numerical coding. So it's basically like using G code and M code. You're generating the. In case of CNC, we use G code M code to define the tool path. So in tool path generation is basically CNC G code M code. In case of NC programming, it's nothing but you're putting the command in the computer by some language which is understandable by the computer. Or if it's not a computer integrated machine, then that machine should understand what you're putting. So just for an example, if you are using an drilling process, then you can just set the drill bit rotation speed. You can set it if it's going to be clockwise or anti-clockwise, and then you start the manual drilling. You pull the lever and slowly you come down to the material. So it's kind of the input that you're putting in the machine. Like that, if your machine understand a code, a numerical code, you can put in the machine so that it can understand what type of heat treatment is going to be done, or what type of stress relieving, normalizing, or aging, what needs to be done. So it's the NC file. NC is numerical coding, and
So here,
CNC is computerized numerical coding.
so is heat treatment done to relieve the residual stresses here?
Yes.
Okay, so during phase milling, what happens to the temperature? Will it increase or
No,
decrease?
no, there is no
Ah,
such relation or there is no such concern about the temperature rise at the time of phase milling, because after milling, there is no such significant temperature rise in any normal metal. It's just done to even out the surface or to make the surface planar or tilted or whatever is needed. After milling, you don't actually increase the temperature much. So that is not the concern of in this study. What he was discussing is after additive manufacturing, we are going to get a very high high temperature part. So what will happen in the at the time of phase milling? So the answer is if your heat gradient is very high, then your cooling rate is also high. So even just after the deposition temperature will not be more than 300 to 500 degrees centigrade. And if it's 300 degrees centigrade and the argon gas is also continuously fed, it will come to 100 degree very easily. And by that time, you can set the computer or the machine can set the part near the subtractive machine, and the subtractive tool can come down and then it can fix the position where it will start its machining. And by that time, it will reach the lower temperature. If not, then you can put some dual time. So that's the answer. Do you have any more doubt?
no, no.
So now it's about the process parameter for the MIG process, the power, the power means here we are working with arc. So arc, voltage, current, these are the main power concerned process parameter. Then filler, where it's gonna be the consumable wire or it's gonna be the off-axis fed wire. So in both the cases, the wire diameter and wire feed rate are the most uh, important parameter. Whereas for a constant process, you are going to use the standard wire, which will have only one diameter. One is 1.2 mm. So that wire is also being used. So wire type is not a process parameter because you cannot change it, but wire type is something which is deciding the process parameter. So wire type means the material composition, coating, coring, like what is the composition, what is the melting point, what is the heat diffusivity, heat conductivity, thermal conductivity mainly, thermal coefficient of expansion, then heat diffusivity, weightability, These are few parameters that will be directly related to the material composition on the material type, and depending upon which you will fix the process parameter. So that's why it comes under the process parameter chart. Then gas. So if you are putting the appropriate amount of gas, you are going to protect the process from the contaminant and the atmospheric moisture and oxidation. But if you are putting more gas than required, then you can eventually disturb the process, disturb the melt pool. Gas has also another work, that is the fed gas also maintain the melt pool shape. The melt pool shape is something from which you are getting the final bead geometry and the final bead property. If your melt pool shape is distorted, you are going to get some porosity and crack and residual stress as well. So gas is very important. How much liter per minute gas you are flowing, from which direction you are flowing the gas, because if it's off axis, it should not happen that the gas is actually flying away the droplet that is going to come, that was supposed to come to the substrate. Then deposition. So layer thickness will be given by the slicing itself. Then bead width, it's something we will measure, and then we will decide the overlap percentage. And depending upon the overlap percentage, we'll get the final width of the layer. Then we'll decide the layer thickness, and it will depend upon the bead height and how much reinforcement height means. So if your bead height is 1 mm, will be your, is it true that your layer thickness is also going to be 1 mm? So it's not true. It depends upon material to material, how you are going to remelt the surface, how your material is going to be weight, like how, what is the weightability. So these are the parameters. Then as we are using the torch as a tool, so the distance between nozzle to the base plate, what is called stand-up distance in other process, is called the arc length here. That is one very important process parameter. Then distance between electrode contact tip and base angle is another thing, because from the nozzle, the wire will come out of the nozzle, and the whole wire is not melted, only the tip of the wire is melted. So there is this arc length is between these distance between contact tip and base plate, and this is mainly the SOD. And torch speed is nothing but the deposition speed. If you remember the definition of deposition speed from FDM, this is the same as torch speed. Path.
Actually, we use a term called arc length in welding.
Yeah.
How we can relate that to this?
So can you tell me that when we increase the arc length, what happens, and when you decrease the arc length, what happens? If you just recall that concept, that
Yeah,
there is one type of material deposition or globular transfer or spray transfer or short circuits transfer of the material. And now if you increase the arc length, your droplet is going to be disturbed, and it's going to take more time to reach the substrate. And if you increase the length more, then it's not even going to reach the substrate. In between, it can fly and it can get distorted, right?
yeah. That is
If
why
you decrease,
a particular amount of the arc length, like 1 mm,
yes,
like that, not more than that.
yes.
Uh,
So the same concept here also, because in welding you are depositing only one track, but here you are going to deposit multiple layers. So when you are printing one layer, first layer, maybe your arc length is 1 mm from the substrate. So for the next layer, you have to pull up your nozzle by 1 mm, because now your substrate is the previously deposited layer, which is already 1 mm thick.
yeah.
So like that, you have to maintain a constant arc length and deposit. And path is nothing but the scan strategy that we call in LPBF process, how you are going to fill the area if it's a solid cube. So this is the component, multi-layer, single bead first, then multi-bead with some overlap, then multi-layer with some overlap in between. It's for the sake of presentation. It was made like there is distance between multi-layer. It doesn't look like this. And the final component will be this dense. So from this picture, you can see there is bead height, there is bead width, and bead height and width is very important. So now I have one question for you guys. Can you tell me that how did this bead penetration depth will influence my next layer deposition? This is a very easy question.
How the penetration depth will
How this penetration depth is going to influence the next layer deposition?
If penetration depth is more, the next layer deposition means the top
the
surface
substrate
of the
also
bead will
involves
be
in
One
melting.
by
height
one.
of the bead height will be less if the penetration depth is more. So it will be easy to deposit the next layer.
It's not, yeah, you are correct. But what I'm asking is how this penetration depth or whether this penetration depth is important for the next layer deposition or not. Think about the previously deposited layer.
Normally in additive manufacturing, we don't require more penetration depth, no?
If we are talking about the substrate, yes.
Yeah. No, to confirm a good bonding between the layers,
A
this
little
penetration
penetration depth is important, but not a lot.
a lot is not
Yeah,
required.
yeah.
So that's why that is based on the kind of polarity we are using, whether it is uh, DC, EN, or
So yeah, but if
that
you
man.
are talking about the one where your substrate is going to be positive, there you do not even have to put that power because your substrate is getting the heat. So a little heat can do the job. Little less heat can do the job.
Yeah, for additive manufacturing.
Yeah, yeah, for that.
So that's why we use DC EP. Yeah, I think
Yes,
we use reverse polarity.
yeah.
Penetration
So
is we want
yes,
small.
yes, yes. So the question I asked is a little bit different. So this penetration depth is basically giving us how much substrate is going to be melted along with that wire, like at the time of the layer, that particular layer deposition. So if I consider the penetration depth, then only I can calculate that how much top surface of the first layer is going to be remelted at the time of printing of the second layer. So this dilution is not that difficult, not that complex or concerned thing when you're printing just one layer. You can you can cut the layer from the substrate, and substrate bonding is also important. So dilution is okay. But when you're talking about the next layer deposition for the second layer, your first layer is going to be remelted again. And if you are
It is
remelting a
melted.
lot portion, then it's going to
But
be a problem.
yeah, but whether the material is really penetrating into that earlier layer or it is just melted.
No, a little top portion of the, if this is my bead, this top portion is going to be remelted.
Okay.
Otherwise,
While going
how it will
the other
get
layer,
fused?
it is melted, but the in while depositing the next layer, so
Mhm.
whether that new material is going to penetrate up to this much depth
Yes, yes. Otherwise, how your
or
second
it
layer is going to be
stopping.
bonded with the first layer?
Yeah, some sort of what is called okay, mixing kind of thing may happen.
Yes, mixing is important. Otherwise, how your second layer is going to be bonded with the first layer?
Yes.
Yes. So that is the reason. So now, yes.
In
Ma'am,
case
so
of
the
polymer,
second layer, will it overlap this bead also?
Yes, yes. Even see, even if you are going to put your layer height from here, when your droplet material is coming, it has to be bonded with the next previously deposited bead, like right? So at least this much portion will be remelted because of the droplet of the wire which is coming to be deposited. Otherwise, how the layers will get bonded with each other?
Okay.
Is it clear or you have any other doubt?
So some portion of the bead height, which is that means the top portion of the bottom bead will get remelted, and the next bead will
Yes,
come over it, right?
yes.
Okay.
In case of wire DD or powder DD, it can be one layer, but in case of other DD process, like not DD, in case of LPBF, it's even 2-3 layers. Previously deposited 2 to 3 layers, because there the heat is even the laser power is less, but the spot dye is even lower, and your layer thickness is very less. So it's around 2 to 3 previously deposited layer.
so what it happens is diffusion happens.
Sorry.
So while we are depositing the weld metal onto the substrate, so any diffusion happens. That is what.
Yes, diffusion is this penetration depth, no?
Yeah.
And this is important for welding also, no? Welding will also have that penetration depth. If your metal substrate is this much thick, you need the penetration depth to be here. But in case of additive, this much penetration depth in substrate is enough, like this much. Any more doubt?
Okay, proceed.
Good. Okay. So like that, if you proceed more, then you start getting the equation by which you can calculate that from which distance your next bead is going to be deposited. So whether it's from here like 50% overlap, or it's going to be 10% overlap, or it's going to be 90% overlap. So you have to calculate the bead height and width. And as the bead is parabolic in nature, you will get the equation how you're going to print the next bead. You have to first measure one bead, and then you can print the whole layer by overlapping the beads. So these are the proof of concept, how you're going to decide. One thing I want to mention is your bead should look like this and not like this. Because when you're going to the next bead, your next bead will look like this. And if you are printing this type of bead, then your next bead is going to print like this.
It's like a parabola.
Yeah, but here it's like a circle. It's like a parabola here. So this is the porosity you are going to get in this configuration. So this is not needed. This will be a good bead. Okay. So obtuse angle, it should not be the obtuse angle in the contact angle. So this is the contact angle. So it should not be the obtuse angle. It should be the acute angle from here. Okay. So that will be considered as a good bead. So first you have to identify the height and width. And when you get this type of bead, you can start calculating what will be the overlap. So these are the equations. So I'm not going into deep in this slides further, because you will get the maths based formula that I'm also going to discuss in my PPT of previous year question. So next is the tick process and plasma. So instead of arc, you can use the plasma as well. So it's gonna be the same thing, only instead of consumable wire, you are using the non-consumable wire, and the wire is fed off axis. So this is your off axis wire coming from here. It's the same concept, but the polarity is going to be reversed than what we used in MIG. And then here also another thing, we try to maintain a background current, and then this is the welding current. Welding current is a peak current where your arc is having the highest power or energy, and your metal is going to be melted. But the background current is there to stabilize the process. If you turn off and turn on the whole voltage setup, then because of the inertia, you are not going to get the stable arc for the whole deposition. So that's why we maintain a background current. And then in pulse mode, we get the peak. We give the peak, and at that peak current, we get the deposition. There's a shielding gas. The shielding gas also maintain the melt pool shape. It also avoid any contamination or moisture entrapment and porosity, oxidation. But due to the gas feeding, we also get some gas entrapment and porosity, but that is not very much. That can be avoided as well. So it's almost the same thing. With the same way you can print, only the wire is coming from another source. So now I think we can start discussing on the previous year question if you do not have any other doubts. And in these questions, as usual, I'm having two previous year questions, like two subsequent years of NPTEL question sessions I'm having. So a lot of question I'm having. So let's start discussing about them. So you can try answering them. In case of MIG-WAM, to produce a less penetration, which type of polarity is preferred? Just a guess. Well, maybe.
It is reverse polarity. Is it reverse?
Yes. Yes, we already have discussed. So second question is, in CMT, big welding process, CMT is called metal transfer, where the drop detachment is obtained by. I think for this question, you need to see the recording. So the answer is the retraction of wire. By the pulsed way of retracting the wire, we get the short circuiting, and we get the high peak current, and we get the metal to get soften up and deposit over the metal, which is called a cold metal transfer.
It is short circuiting. Is it?
Short circuiting, kind of. Not exactly, but it's just like it will touch the wire, it will touch the base plate, so there will be short circuiting, and then it will retract, so there will be a high spark, and because of the spark, the metal will get deposited. So it's called the
Actually,
cold metal transfer.
I have a doubt. How actually short circuiting happens?
How?
Short circuiting happens only while it is separating from
Short
the
circuiting
substrate.
is Short circuiting means when you uh, touch both the electrodes together, it starts flowing the current from it. So that is the short circuiting.
Okay, that means current will flow.
Yeah, current will flow. But in case of DD, if you understand, the heat energy directly interact with the metal and it melts it. But in case of CMT, it's cold metal transfer, because the heat is not directly, the heat means the electric voltage or current is not directly uh, interacting with the metal. It's when we are retracting it because of the spark, we are getting the mass transfer. But it's not like the MIG process where the continuous arc is coming and it's melting the metal.
Yeah, that is intermittent.
Intermittent, yes.
But that happens mechanically. By that means some uh, provision for retraction of wire is to be made
Yeah, yeah.
from
So that
outside.
outside, yes. So for outside the machine, so in the torch that you are using here, in case of CNT, is connected with the CNC machine where the code is given that for the few milliseconds, the short circuiting will be there. And for after few milliseconds, it will retract the wire from the base plate. So because of the high current flow, because of the short circuiting, there will be spark. And because of the spark, there will be metal transfer. In case of this process, now the process is very stable. The spattering is very less. So it's a very kind of controlled process, but it's difficult to control because of the retraction. But if you can control the retraction and control the short circuiting, then the overall process is very much controlled.
No, it is a kind of alternate uh,
No, alternate current is when you give the current in the opposite poles in few fraction of seconds. But this is where we are physically retracting the wire.
yeah, physically retract means the wire moves along z axis
Yeah, yeah, yeah. It will move out,
by some
move up.
by some means, maybe
Yeah,
CNC.
by some the CNC and the tool that you have attached to the nozzle.
Yeah, again it will come closer to the substrate and it will stay there for some time and again it will be retracted like
And
that.
this sometime is in millisecond or like that.
Yeah. During that, when it is retracted, then only spark produces.
Yeah, yeah,
When it is short circuited, only current flows.
yeah. So when
No,
you retract the metal, now the electrons were flowing. So now when you retract the metal wire, the electron will try to flow because the current is already there. The current flow is already there.
there. It will try
So
to flow and
that's
then
why the electron will jump from one electrode to another. So that's why you will get spark.
melting takes place only when there is a gap between
Yeah,
the wire
yeah.
and
Basically softening the metal and the metal is transferred, mass transfer.
yeah.
Yes. So now we have the third question. With regard to MIG WAM process, select the correct option.
Non-consumable electrode is not known. It's not correct. Power surface
So
is it
the
B
Is it
current from the welding
machine is
machine
changed?
is changed by the rate of feeding of the electric wire.
The remaining three are not correct. Current from the
Sorry?
welding
Yeah. Non-consumable is obviously not true. Then
not
straight polarity is,
penetration is more in reverse polarity. Sorry,
yeah,
penetration is not in reverse.
but the
Uh,
penetration is not small here.
yeah, actually, the power supply is of constant voltage.
Yeah, yeah.
Current from the
We are
welding
putting the
machine
voltage in MIG.
of
In TIG, it's like the background current and the peak current concept.
rating of the electrode wire. Yes, if the feed
Yes.
increases, obviously current we need to increase.
Yes, yes. Yeah,
Yes,
so now we have the next question. Which of the following best describes the cold metal transfer process? A process where the welding wire. So, yeah, these are the options.
this is where the welding wire is constantly heated to Is it B or
B.
none of the above? Controlled transfer of droplets from the welding wire to the workpiece.
Option B, man.
B.
So, a process that involves a controlled transfer of droplets from the welding wire to the workpiece by the retraction of wire. Cold metal transfer is all about first short circuiting and then retraction of the wire. This
Yeah.
is the main phenomenon. So, which
Retract-
material is typically used as a feedstock in MIG-WAM? It's very easy.
Typically used as the feedstock in MIG van. It is
Feedstock
normally
means
opposite
what you're
wire.
printing.
Wire, wire no.
Yes, it's the metal wire.
Wire pool.
Yeah. Feedstock
Rod in the
means
sense,
what you're printing.
Means feedstock will get melted. Is it, man?
Yes, feedstock is your raw material for the printing.
yeah. Rod in the sense, it is not like continuous, no. It is just
No, rod means its diameter is way too high.
I mean, in
yeah.
case of TIG, will it be tungsten electrode?
In case of TIG also, it's metal wire. Tungsten is the electrode. It's also a wire, but tungsten is not getting melted. But the
Hmm.
feedstock is getting melted. So the feedstock is also a metal wire.
Okay,
In
so
case
what
of
is the use of tungsten in TIG, man?
Tungsten in TIG is to produce the arc.
Okay, when
Tungsten
electricity is
is your
passed through
electrode.
tungsten electrode,
It's just the TIG welding. Tungsten is the electrode to maintain the arc, and the wire is fed off axis.
it's non-consumable. Separately, we have
Yes,
to feed the wire.
yes. There is two metal transfer, or there is two type of welding only, na TIG and MIG. So the same concept.
so in plasma, it will be
Plasma is similar to plasma is a heat source. There is that is also non-consumable type of wire.
But what is the difference between TIG and plasma, madam?
Okay, arc is basically the jumping of the electrons from one to another electrode, and plasma is basically when you discharge the electric current in the gas disperse into the atoms and then in the plus minus polarity, and then from the plus minus polarity we get the plasma. It's basically the cloud of the ions. Ion cloud is basically the plasma.
The temperature will be very high. Then
Yes, plasma temperature is very high. Basically, first there is a gas. We discharge, so we are basically ionizing it, and after ionizing, we get the free electrons. So the ions and this free electron cloud is basically the plasma. In
in
electron
TIG,
beam, we just give the electrons with a very high speed by focusing it using magnetic lens. Laser is where the photon is coming. Arc is where the electric current is basically going through the electron movement. And this is free electron and ionized gas, which is coming out of a nozzle. Basically, plasma is also called as a fourth state of matter. After gas, discharging the gas, we break into ions. So that is the plasma.
so metal wire is the feedstock in plasma process of means.
Yes. WAM
Okay.
means wire arc additive manufacturing. That means wire is the feedstock. Feedstock means your raw material. That is the wire, as the name says. Now, how you are putting the energy, that is different. In case of MIG, your wire only carrying the energy because that is the consumable electrode. In case of TIG, your electrode is different than your feedstock. And in case of plasma plasma, it's different. And in case of CMT, again, your feedstock is the one who is getting the short circuiting and retraction. Cool. So here is our next question. In MIG welding, what type of power supply is mostly used?
Constant voltage.
So in case of MIG, it's constant voltage. In case of TIG, we are doing the current thing. What kind of defects can result from improper shielding gas coverage in MIG?
Proper shielding gas. It is porosity. I
Yes,
think it porosity.
yes. Delamination, cracking, and warping is all about the energy density that you are putting. The porosity is the one thing. What is the typical polarity used for TIG?
For TIG, it is opposite to MIG, no?
Yes,
Direct current electrode positive. No.
negative.
Direct current negative. We call
Yes.
that as
Electrode negative. Electrode means the one
straight.
that is, we have put the wire, that is the electrode. I'm calling the wire as an electrode again and again. Na? So negative means that is not going to be melted. So that is the TIG welding. Good. Then in a single bead experiment using MIG WAM, the bead cross-section profile above the substrate is found to be symmetric parabola. If the base width is 6 mm, what will be the optimal value of the step over distance between two constructive beads? So this is the formula. I would suggest you to write down the formula and you can use it later on for practicing.
Is 2/3.
And for last week assignment, there was a question.
Yes.
In microcasting, the arc is generated between the MIG welding gun and options were substrate, sacrificial electrode, tungsten electrode.
Yes.
So, what is the answer, ma'am?
I also forgot the answer. I have to check.
I
is not.
have given substrate, but it was wrong.
It is not substrate. Myself also I wrote substrate. It is wrong. But another
They have
electrode.
given that it is tungsten, but I don't know how.
Yeah, it is between MIG and plasma.
The question was, can you repeat the question? I'll note down.
In microcasting, the arc is generated between the MIG welding gun and dash. The options are substrate, sacrificial electrode, tungsten electrode, none of the above.
Okay, so it's the sacrificial electrode.
But the accepted answer they gave was tungsten electrode, ma'am.
Tungsten electrode.
Yes, ma'am. But
The
what I put was
the
substrate, but it
tungsten
was wrong.
electrode, and what is the another one between the current?
Three options are substrate, sacrificial
No, no.
electrode.
The question in the question. What is
Uh,
the connection point?
in microcasting, the arc is generated between the MIG welding gun and dash.
Actually, it is between MIG and
Okay.
plasma.
So it's MIG welding gun. That means the metal is going to come from the MIG welding gun. That is the sacrificial electrode. So now we are making the circuit between the sacrificial electrode and the another one to make the circuit. So you have answered as substrate, and the answer was stick gun.
Answer was wrong, ma'am. Substrate.
Yeah, it should be the substrate because if I'm
Um,
making
it is,
the.
But they
it
have
is not
not. They have
substrate.
given
Not
0 score
substrate.
for us.
So did you attend this recent this live session with the organizing committee?
No, ma'am.
There are this monthly live sessions with the organizing committee because I'm also not sure about the answer. I can search about the answer and let you know in the next class. But by that time, if you have any those mails that attend that session and you can ask.
Yeah. I have solution for this. Even myself, I uh, opted for substrate, but
Okay.
I got a clarity that in microcasting, actually the
Hmm.
loop is between MIG and plasma. Work part need not be electrode.
Okay.
We are giving we are not giving any connection to the work part. One
Okay.
connection that is positive we are giving to MIG and negative we are giving to plasma. So plasma means it consists of tungsten electrode, I think. So in between
Okay.
MIG and plasma, so you have that uh, arc generation and all. So in that process, that electrode, the MIG, it carries the consumable
Hmm.
electrode that undergoes melting.
Then it should be the tick gun.
Arc is generated between MIG and plasma. So work part, though it is subjected to some kind of melting, but it is not a part of the loop.
Yes.
That is what
Then
it
it
is.
should be. Yeah,
Yeah.
that's this is
In other
one
welding,
answer.
actually, work part is a also one electrode. Work part we treat as electrode, but here it is not. We are not. It is not like that.
Okay. Yeah. In MIG-TIC,
I
it's the
noticed that in
substrate.
my notes. Yeah.
But if it's the combination of plasma and then MIG, then the plasma will be the second electrode. That means
So
from the tick gun, the plasma is getting generated. So
in plasma, normally we use tungsten as electrode.
in plasma, actually, we don't need a electrode, conventional electrode, but where the electrode will have the arc. But tungsten can be used to produce the current because we are discharging the gas here. So to produce the current, you can use the TIG setup.
Yeah, tungsten, because
Yeah,
it is having
tungsten.
very high melting point.
Yeah.
So that is that. Even I lost mark.
Oh, okay. Yeah. So now for the 10th question, the answer is given here. So the optimal value of step over is equal to two-thirds of the beat width. So according to that, your answer is going to be 4.
Yes.
Next, in a MIG welding based wire arc additive manufacturing process, the following process parameters are considered. Blah blah. Sorry, what happened? Okay. So the deposition rate is called the DR, and with DR, we get this equation: cross section, velocity, and the density. So, sorry, not the velocity, but the you can call the velocity as the torque speed and the wire feed rate as wire feed rate. So velocity is the deposition rate, but VW is the wire feed rate. So like that, you can uh, calculate the AW, and by multiplying it with rho, the density, you'll get deposition rate in gram per minute. You can note down the formula. Any doubt in this formula? Placing the values? No. So the next question is for the process explained in equation 11, what will be the bead width The bead width is also having some relation with the diameter of the wire that you are using. The feed rate, obviously, and this is how you can get the height we already know. And also the velocity of the process that is called the torch speed or the torch velocity. By that you get 4 pi as the answer. Next question is for the process explained in equation 11, what will be the value of optimal step over? So this is the formula. So the step over is equal to 2/3 of the bead width. We already know. So this is the answer. Similar question. For the process explained in equation 11. Just a second. So now, what will be the approximate value of the minimum required power? These are the equations. It's a very big equation, but actually it's not a difficult equation. So we can calculate, we can put the values and we can calculate the power. I think it's better to note down. If you have any doubt regarding the parameter, you can ask.
AW and all, where is it? Oh, it is based on question 11, is it?
Yes. Now we have the 15th question. In TIG WAM process, a rotating wire feeder is often used to achieve rotating wire feeder means in TIG you are putting the wire from off axis. So if you are going from here to here, there will be one pattern in the process in the metallographic properties. And when you are going from here to here, your complete melting process changes. Because if the wire is coming from right direction, you're going from left to right. And now with the same configuration, you're going from right to left. The heat interaction is different, right? So that's why the rotating wire feeder, like when it's going from left to right, if the wire is coming from right, then when it's coming from right to left, the wire is coming from left. To maintain same type of configuration and property in the melt pool and deposition. So what can be the cause? It's there to minimize the directional solidification, so omnidirectionality. Which of the following wire feeding mechanism is preferred in TIG?
Side feeding.
It's the front feeding. In side feeding, it's like when you're going from one left to right, the directionality is present. But when it's front feeding and you don't have the rotating thing, it's better. Whenever you're going from left to right or right to left, it will be similar. If you are using back feeding, then for some corner or some tilting or something, or some like the moving the axis, your wire may hit the torch. So that's why front fitting is better. Now consider a block deposited by MIG. In this block, the microstructure is usually dashed too close to the newly deposited layer as compared to the previously deposited layer. Try. Try. Think what is happening in the first layer and the second layer. So it's the finer. The microstructure of the newly deposited beads is always finer because of the high cooling rate. That's the simple thing. In MIG process, usually the adjacent layer got delaminated due to it's the incomplete melting of the substrate. So that's why the penetration depth in substrate is important while printing the first layer. So now comes this popular sum. In thin wall, a thin wall has to be built in MIG-based process. First, a single bead experiment was performed on the flat surface. A circular profile on the bead was obtained. Find the height of the thin wall after deposition of 15 layers. So this is the equation how you can evaluate if your 2 is the bead height, how much you should take the overlap as so that you can get the total height. So you can eventually calculate the overlap as well. So this is the formula. You can note down this formula. This question is consistent throughout the years. So you can have this type of question. So it's better to note down. Which of the following is most suitable metal transfer method in MIG? Is the pulsed metal transfer. In MIG welding process, the straight polarity gives the bead penetration while reverse polarity gives dash. Quick guesses. It's when straight polarity gives large penetration where reverse polarity gives the smaller penetration because we are lowering down the power there. Which one of the following is most suitable metal transfer in MIG? It's pulsed, already answered. The cold metal transfer MIG is one of the preferred process due to it's easy. Try to guess.
Low heat input.
Yes, it's the only reason why we use CMT, why researchers invented CMT. Because of the low heat input, the spattering is actually less. The substrate dilution is also optimal and your process is controlled. In the CMT make process, dash motion of the wire assess the droplet detachment during the short circuit. What is it? You know the answer. In CMT, think
Retracted.
about what is CMT.
Retracted.
Yes, it's the retraction. In a single bead experiment using MIG-WAM, the bead cross-section profile above the surface found to be symmetric parabola. Same question, width into 2 by 3 will be the height, the step over, sorry, 2 In a MIG welding based wire process, these are the parameters. So this is the same, that's why I wanted to show you. This is the same parameter that you are, this is the same formula that you are using to get these problems. So you should practice these problems home after the presentation, after today's class. And I always upload the PPT in the given Google Drive, so you can always find the solution and the problems. For the process explained in equation 8, what will be the bead width if the bead cross section profile above the substrate is found to be symmetric. So the same question with the same formula, it's the 2 pi. You can find the formula from the previous year question that I already solved. For the process explained in equation 8, what will be the optimal step over? Same 4 pi by 3 using the 2 by 3 with formula. So it's 8 by 6, that means 4 by 3. For the process explained in 8, these are the specific heat and all. The same formula with the efficiency and the power that is going to the base plate. For penetration depth, that is going to the bead. To have the bead height, we plus it, we get the power that is needed. So a range is given. In between the range, if you are marking the value, you are good to have the marks. If the residual stress in the part produced in MIG-WAN process is more than the UTS of the material, then what will happen? And if the residual stress is less than UTS and more than YS, then material will have what? I will answer. It's a little bit tricky. So if the UTS, that means ultimate tensile strength of the material, when WIM processes where the residual stress in the part is more than the UTS, then crack will happen because residual stress is so high, then that when you applied the load, the cracks initiation will start out of the residual stress and the cracking will happen. If the residual stress is less than UTS, so it's not going to the ultimate tensile strength, but it's going to the YS value, then the warping will happen. In MIG-WAN process, the raw material induced porosity are due to unstable process, and the process induced porosity are because of the surface contamination. So raw material induced porosity is because of the unstable melt pool, basically. And the process induced is basically the contamination by which the porosity is coming. It can be gas entrapment as well. Or it can be because of the high input, the melt pool became unstable. That can also happen. In MIG-WAM process, a layer is deposited on the substrate which was not cleaned properly. So the defects are likely to be happen is the residual stress because there will be inclusion or the foreign particles that can take away the heat and that can create defects in the part. In MIG-WAM process, usually the adjacent layers got delaminated due to same incomplete melting of the substrate. In TIG-WAM, the rotating the wire feeder is because of the omnidirectionality. I'm going fast because today I'm in the middle of a conference. I have come for a conference to present my paper. So that's why I'm going a little bit fast today. And also these questions are already been discussed earlier. So in TIG-WAM, the wire feeding is separately controlled because my electrode is not consumable. In WAM, the inert gas is used for ionization and establishment of the arc. That is the plasma, because gas ionization is what we do to get the plasma. Which of the following wire feeding system is preferred? So it's the front feeding. And this is another unique question. So in TIG-WAM, which of the following graph is suited more? So it's between the boundary radius of the arc and the maximum intensity. So it's this exponential. You can note down this graph as well. So like that, here comes the end of my PPT. For today, I am ending the session a little bit early today, but we can extend the session more in my next class. I also have the Mentimeter question for WAM that I'm going to show in the next class. So We can discuss more about VAM if you need it. Cool. We can end here.
Okay, ma'am. Thank you.
Thank you. Thank you for attending. We'll meet in the next class.